Right, Assalamualaikum and good day everyone. So this is the recorded lecture which is on the topic of digital codes and logic gates. Okay, so let us start with this one. Lecture material is not that many. It's only cover for up to I think few slides. So hopefully we'll be able to finish it up real quick. Okay, so for this topic is on digital codes and logic gates. So let us begin. Right. So what will be covered for this week is on digital binary codes and logic gates. Yeah, digital binary codes and logic gates. Okay, so for this digital binary codes, we will cover on the binary coded decimal, SK2 codes and gray code. And for the logic gates, this is the simple representation of the basic logic gates, which is the AND gate, OR gate, NOT gate, NAND gate, NOR, XOR, and XNOR gate. Okay, so what does it mean by digital binary codes? Okay, so these digital binary codes is actually used for the coding for the normally for the computer, where we represent numbers, letters, and word is being represented by a specific group of symbol. Okay, so these symbols is being encoded. So this is what we call as digital binary codes. Okay, so the digital data is being represented, stored, and transmitted as a group of binary bits. Okay, so this group is called as binary codes. Okay, the binary code is represented by a number and also a combination of alphanumerical letters. Okay, so what is the advantage of having these digital binary codes? Okay, first is that it's very suitable for computer application. Second, for digital communication, especially using your telecommunication and your mobile telephone, the anything, your printer, laptop, and all that, they are using digital binary codes. Yeah. Okay, and then for these binary codes, it will be easier to do the analysis and designing the digital circuits, right? Because the only output that we have is either 1 and 0, so it will be easy in terms of the output implementation. Okay, so the codes can be categorized into four categories. The first one is what we call as weighted codes. So for weighted codes, it has weighted code and non-weighted codes. So weighted code yang maksudnya code yang ada pemberat lah. Maksudnya setiap bits tu dia ada dia punya pemberat yang tersendiri. For non-weighted codes, which is it does not carry any base power for any bits. Right, and then for the second category is what we call as binary coded digital codes, BCD. Okay, and then the third one is alphanumeric codes, and finally, the fourth category is on the error detection codes and error correcting codes. So we go for the first category, which is on the weighted binary codes. Okay, so for the weighted binary codes, all these binary codes will carry a specific weight, okay, which is if let's say that so the codes can be expressed from digital 0 up to 9, okay, so which is in 4 bits group. So let's say on this example over here in decimal is 24. So this 24, if let's say that we change to binary codes, which is we change to binary, so each what we call these 4 here can be represented in 4 bits binary codes, and 2 also can be represented in 4 bits binary codes. So how to do this variation is what we call that we can do the splitting method, where these for 4 bits each of the from starting from the your left side is have the power of 2 power 0, and we start to increase the power. So from, let's say here, let me write it. Okay, so we have 4 bits. So for 4 bits, So we will have 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. So your most left will be equivalent to 2 to the power of 0. The weighted will be 2 to the power of 0. Your most left will be has the highest weighted, which is 2 to the power of 3. Okay, so 2 to the power of 3, we know that will be equivalent to 8, 4, 2, and 3. Okay, so if let's say that you want to change to that from this example here in decimal is 4, so we can see that so the position that have weighted power of 4 will be close to 1, while the rest is 0. That's why you'll be able to get this one here, which is 0, 1, 0, 0. Same goes to here. We want 2, right? So at position of 2, base power of 2, that then we can write it as 1. The rest make it as 0, so that it will be equivalent to 2 in decimal. Right. So for these digital binary codes, which is in the second category, BCD, what we call as BCD, this BCD is a non-weighted what we call non-weighted codes because it doesn't carry any weight. Okay. So this BCD can be represented from 000, 4 bits, yeah, from 00 up to 111. Okay. So, but in this VCD, only the first 10 of the VCD, which is from 000 up to 1001, are normally being used, or what we call as a valid BCD number. Meanwhile, the rest of the combination, which is after 1001, which is starting at 1010 up to 111, is what we call as invalid BCD number. How to make this invalid BCD number become valid? Okay, we will look at that in the next slide. Right. So first we look into the advantage and disadvantages of BC codes. So for the advantage, it's very similar to decimal system. So it will be easy for us to what we call familiar with the numbering in BCD, which is the number will start from 0 up to 9. Okay, so for disadvantage, in terms of the arithmetics, which is the in terms of addition and subtraction of BCD number, is it will have different rules and it a bit complicated. Okay, and normally this BCD needs more number of bits than binary to represent the decimal number. So which is this will make this BCD is less efficient than binary number representation. Okay, so let's see on this example over here. Okay, so we need to display for BCD in 4 binary codes, okay, which is in decimal will be from 0 to 1, yeah, 0 to 9, sorry. Okay, let's say we have this example over here. We want to convert 15 base 10 to BCD. Okay, so we need to group of 4 binary codes. So for one, this is 2 to the power of 3, 2, 1, 0, 3, 2, 1, and 0. Okay, so which is 8, 4, 2, 1, 8, 4, 2, 1. So this is how you change from your decimal to BCD number. Okay. Okay, this is in terms of the BCD arithmetic, which is involving the addition in this example, this slide over here. Okay, for the rules when involving the BCD addition is that this one you need to focus on. Yeah, if a 4 bits sum is equal or less than 9. Okay, this is a valid BCD number, which is, for example, like is 4 plus 3, you get 8, right? 8 is less than 10, 8 less than 9. So this is a valid BCD number. If these 4 bits is sum is greater than 9, or it has a carry forward, okay, will be a carry forward will be generated. okay, it will lead to what we call as invalid BCD number. So how to make these invalid results or invalid addition is become valid? By adding this, which is this one here, by adding 0110. Okay, after we add this 0110, then our answer will become a valid BCD number. Okay, so in this example over here, we have these two binary number, right? So first thing is that you need to change to decimal in order to see whether your addition is valid or not. Change to decimal. This will be your first thing that you need to do. Okay, and then you can perform the addition, which is okay. Look at um, the rightmost, which is 3 plus 8 is equals to 3 plus 5 is equals to 8. 8 is less than 9. So this is a valid BC number. Okay, and then 2 plus 1 is 3. So we know that this addition is a valid addition. No need to add 0110. So you can just perform a normal addition between these two binary number. 0 plus 0 is 10, right? So 0 and bring the 1 to the next. 1 plus 1 is 10. Again, 1 plus 1 is 10 here. Okay, so you will get your answer is 00111000 BCD. Okay, so let us give a try on this BCD addition. Okay, we have a 100 plus 100. What you need to do is that first you need to change to decimal. Don't forget that in order to see, okay, change to decimal first or these two number to see whether you can perform a valid or invalid BCD number. So if valid, okay, then no problem. You can just perform just a normal addition. Okay. So if it invalid, what you need to do is that you need to add 0110 into the addition and then perform the addition. Okay, so let us see on this example in the next slide. Okay, so for A is 1001 plus 1001. Okay, so what is this number in by a decimal? 1001. So we have 8, 4, 2, 1, right? So 1 multiplied by 8 is 8. Okay. 0 plus 0 plus 0 and plus 1. So you have actually 9, right? So this number in decimal is 9 plus 9. So 9 plus 9 is equivalent to 18, which you need to bring forward, right? So when you need to bring it forward, so this is become invalid BCD number, yeah, invalid. So what we need to do is that later we need to add 0110 in order to make this BCD addition a valid results. So first we just do the we call the addition. Okay, and then later add 0.0110, which is equivalent to 6 in decimal, and then you perform the original, the actual. Okay, so this is your results here. Okay, so now let us try on B. Okay, B is 000. Wait. Oh, sorry. It's only okay. The original number that been given is um. Okay, let me see first. Okay, 1, 2, 3. Okay, 10110, right? Okay, plus 0001001. Okay, you need to change what you need to do is that you need to change to um, a decimal to see whether this addition is valid or not. Okay, you can group of 4. So 1, 2, 3, 4 in one group. Okay, so it will come 0000110. Okay, 8421, 8421. So here is 1, 4 plus 2. Okay, 4 plus 2 is equal to 6. So the first number is 16 in decimal. How about the second number? 0000101. Okay, again the same. So 1, 4 plus 1 is 5. So it's 15. 16 plus with 15, you get 31, right? So just you need to bring a carry forward. So this is invalid BCD. So later you need to add. Okay. Right, just perform the addition first. Okay, and then later add 0110 to make this result is a valid result. Yeah. So this is a valid result for B. So now we go for C. Okay, C is 0.01100111. Is it correct? Yes. Okay. Plus 0.100111. Okay. All right. So first you need to identify in terms of decimal what will be the number for these two binary number. Okay. So 0.11100111. So 8421, 8421. Okay, 4 digits, separate in 4 digits. Okay, so this will be 6, 7. Okay, the next number is 0101, 0011. Okay. Okay, it's 5 here and 3 here. So in terms of decimal, is 67 plus with 53, right? So obviously you need to bring it forward. So this is invalid BCD addition. So later you need to add 0110. Okay. Okay. Add. Okay, this will be the answer for C. Right, so we go for the next category, which is on the non-weighted. So is this for non-weighted codes? There are two representation, which is what we call as access tree codes and gray codes. We will look into gray codes only for this non-weighted binary codes. So for these gray codes, there is no specific weight that being assigned to each of the bits position. Okay, no specific weight, which is you cannot use this 8421 anymore for this gray code. You cannot use this. No, you cannot use this one. Yeah, right? So only one bit changes to the next sequence. Okay, so we will look into two conversion, which is from binary to gray code and gray code to binary. So this is in terms of decimal, this is in terms of binary. So you can see that they are for gray codes only one bits that been changed for gray codes. For it start from 000, okay, and then for when decimal is 1, binary is 001, record is also 1. Okay, but when decimal is 2, in binary is 0010, in Greek codes you change, is 000, this 0 here you change to 1. Okay, and then this one here change to 0. Okay, and then maintain here to the next one here, change to 1. And again refer to the next one, and this one is maintainer. Okay, and then this one here. Okay, this is how the bits from binary and gray codes being changed accordingly. Right, so we look into the first conversion, which is from binary to gray codes. How are we going to convert from binary to gray codes? Let's say we give you this binary number 10110. Okay, this is the binary number 10110. You want to change to gray code, what can we do is that first, the first step is that you need to start from your most left. Your most left, just start from here. Okay, first step, bring down the most left. Okay, bring it down. So 1, so you bring it down, become 1. Okay, your most left, you need to add with the next bit. So 1 plus 0 is equal to 1. So bring the result down. 0 plus 1 is also 1. Bring the result down. Okay, 1 plus 1 is 1, 0. Okay, so which is 1, 0, which is your answer is 1. Your answer is 0. The 1 is being carried, right? So just take the your most right, which is okay, 1 plus 1, okay, is 1, 0, right? Take this one only as your answer in Greek codes. So 1 plus 1 is, take only 0, 0. Ignore this one here. This one here, just ignore. Okay. 1 plus 0 is 1. Okay. All right. So now we go for this is the second example. We want to convert from binary to Greek codes. We have this a number here 11111. Okay, so first step, your look at your most left, bring it down the digits, whether it's 1 or 0, it doesn't matter, just bring it down, no need to do anything. And then starting from your leftmost, okay, plus you add with the next digit, the next bits. 1 plus 1 is 10, right? Okay, 10, 1 is ignored, just bring down the 0 here to your answer. 1 plus 1 is 10, just bring 0. 1 is ignored. 1 plus 1 is 10, right? Okay, just bring down 0. This one, ignore. Okay, and again the same. So in Greek codes, it will be 10000. Okay, so for the next conversion from Greek codes, you want to convert to binary. Okay, so giving these Greek codes, okay, of 10110, you need to convert to binary. Okay, first, again the same thing, start from your most left. Okay, left, start from your left to your right, yeah. Okay, the first, your most left, bring it down the digits, the bits, which is either 1 or 0. Okay, bring it down. And then this answer, okay, you need to add to the next bit. So 1 plus 0 is equivalent to 1, right? So 1 plus 0 is equivalent to 1. So you need to bring this one here down as your answer for your next binary number. Okay, 1 plus 1. Okay, 1 plus 1 is 10. Again, take only 0, bring it down. 1 here is ignore. Okay, so bring down 0. Okay, 0 plus 1 is equivalent to 1. Bring down 1. 1 plus 0 is equivalent to 1. Then bring it down as your answer. So the binary number will be 11011. Okay. Um, okay, this is also the example in order to convert from Greek codes to binary. Again, the same things here. So start from your leftmost is your first step here. Then bring it down is your second step. Perform the addition from your results here to the next bit. Okay, and then whatever is the result, bring it down. If let's say that 1 plus 1 is 10. Okay, 1 here is ignore, just bring down 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 10. 1 ignore, just put the, 0. Okay, so okay, this is one of the passing question. Okay, we will do for question part A, which is it will involve the binary number and Greek codes. Okay, so for this, giving what is the number? Okay, in the question it states that determine the largest number for octal number that can be expressed with 4 bits, and then you need to convert the number into binary and Greek codes. Okay, for octal, so octal, we know that octal is from 0 up to 7. So 4 bits, so 7 is the biggest in octal, right? So 4 bits, 7, 7, 7, 7. So this is 4-bit octal number, the largest 4-bit octal number. So, and then we need to convert to binary and Greek codes, right? Convert to binary and Greek codes. Okay. First, how to convert to binary? We can do the splitting method. Okay. So, octal is group of 3, right? Okay. So, group of 3. So the highest possible base power is 2 to the power of 2. 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. Right? Again, the same for the next bits here, which is we have 4, 2, 1, 4, 2, 1, 4, 2, 1, 4, 2, 1. So in order to get 7, okay, which is you need to put everything equals to 1, because 1 plus 4 is 4, right? 1 plus 2 is 2, okay, which is now it becomes 6. 4 plus 2 is 6. And 1 plus 1 is 1, so it becomes 7. Okay. So the rest also 7. Alright? Okay, let me stop for a while. Yeah.